This is Earth. This is where we live. And this is our solar system. In the grand cosmic neighborhood, the solar system is our home. We have the sun, our star, at the center. We've got 8 planets, a Pluto, an Eris, some other dwarf planets, and a whole lot of comets and asteroids. It's a pretty great home. You've known this home your entire life. However, for just a minute, let's pretend you haven't. Let's pretend you just arrived from a different solar system, from an alien planet orbiting the star called Regulus. You are still 100 million miles out from the sun, and you've decided to take a breather and get a sense for what this solar system is all about. Okay, there's the sun, as the locals call it. Looks like it is 100 million miles away. All right. And then there's... Whoa! What was that? The computers on board our spaceship are reading out that was a planet, popularly known as Earth. From where we are sitting, Earth just passed directly between us and the sun. We must be edge-on with Earth's orbit of the sun. I wonder, if we sit here in this spot and wait long enough, if we'll see Earth again. Only one way to find out. You see those other objects in the sky? Looks like we've got some other planets in the solar system. Yep, there it is. We've been sitting here for 365 days just to be certain. Sure enough, Earth just passed between us and the sun again. Looks like it takes 365 days for Earth to orbit the sun and complete the Earth year. I wonder if this star has other planets besides Earth. Let's get a different angle and see what we find. This looks like a good spot. What a find! According to the computer, this planet is called
Saturn.
Okay, well let's see how long it takes Saturn to complete an orbit. There it is again. And once again, we now know how long the orbital year is. We've been sitting here for a little over 29 Earth years since the last time Saturn passed, which tells us that it takes a little over 29 Earth years for Saturn to complete an orbit. This means that one Saturn year is a little over 29 Earth years long. And if we thought about this in days, it would take a little over 10,000 Earth days to complete a year on Saturn. That's a long time between birthdays. Let's pull back just a little bit more. From this position, we actually can detect all 8 planets as they pass between us and the sun. That's because the orbits of the 8 planets all orbit the sun at the same angle. We are able to see these planets when they pass between us and our spaceship and the sun because we are facing their orbits edge on. What do we mean when we say edge on, you might ask? Well, let's compare it to a hula hoop. A hula hoop is large and circular like a planetary orbit. Now, if you hold it flat and hold it up to your eyes, you will see it edge on. From this viewpoint, even though it is circular, the hoop will look like a flat line. The edge line, you could say. If we look at the Earth's orbit edge on, that will look like a flat line too, and the Earth will move back and forth from one end to the other. And since the sun is right in the middle of Earth's orbit, from our perspective, the Earth will pass directly in front of the light from the sun. At that moment, we will be able to see the Earth clearly, because we are observing edge on. The same applies to other 7 planets. However, there's one thing we won't see. We won't be able to see Pluto because its orbit is tilted at a different angle. Since Pluto, a dark object in a dark sky, never passes in front of the light of the sun, We will never see it when we view the rest of the planets edge on. Hello? Sorry, I'm kind of in the middle. What? What's that? Oh, I'm so sorry. Totally my fault. Yep. Yeah, we'll be right back. Okay, bye. Sorry about that. It sounds like your alien mother got locked out of her house on Regulus, so we're going to have to head back to let her in. It's okay, though. This will give us a chance to really test out our ship's sensors. We've just traveled 77.6-ish light years back to Regulus, and there it is. Now that's a beautiful star. And behind it, way off in the distant sky, is the sun. At this distance, our ship has no chance of seeing the sun's planets with its telescopes. Like I said before, the planets are just too dark in a dark sky. But we can see the sun, and we can detect the planets with other information. You see, the detectors on board our ship are unbelievably good at measuring light from distant stars. They also notice changes in light from a star. One of the great things about Regulus's location is that it sees the solar system around the sun edge on. As a result, it sees every planetary orbit in the sun's solar system edge on too. This is crucial, because although we can't actually see any of the planets, we can observe how they block the light from the sun. That's why it's so important to observe planets edge on. We need the planet to pass right in front of the sun in order to measure the change in light from the sun. There! It just happened! Earth just passed in front of the sun. Did you see it? No? Well, your ship's light detectors did. The detectors noticed that for a short period of time, there was less light from the sun, and then the light returned to normal. Now here's a question for you. Which object won't our ship's sensors be able to detect? Do you remember why? Nailed it! No ship on Regulus is going to see Pluto, because Pluto's orbit is tilted. Strange place, Pluto. Okay, let's move on. You're human again, assuming you were before, and Earth is once again your home. So, let's talk about what human astronomers know about life in the universe. For centuries, human astronomers have been speculating that stars other than our sun might have planets of their own. These planets are known as extrasolar planets. Extra, beyond. Solar, our sun. Planets, well, planets. Planets beyond our sun, aka exoplanets. Perhaps, in other solar systems and galaxies, we'll find exoplanets similar to our own. Large gas giants like Jupiter, or small rocky planets like Mercury. Or maybe something we've never even seen before. However, we don't yet have any spaceships that we can take to other solar systems to look for and count planets. We have to observe from right here, Earth. So, scientists have been building better and stronger telescopes to make up for the incredible distance between Earth and other solar systems. It wasn't until the 1990s that scientists began to discover true extrasolar planets, or exoplanets, based on real evidence. And in 2009, NASA launched the Kepler telescope to detect... what? You guessed it, exoplanets. Now, we have discovered over 3,500 exoplanets. Some are more than 10 times larger than Jupiter, and some are barely larger than Earth's moon. These last few images are just artistic ideas of what exoplanets could look like, but they are nothing compared to the real, stunning images we've captured of exoplanets so far. Like this one. And this one. Doesn't look much like an exoplanet to you, you say? Well, it turns out that even with today's most advanced telescopes, it's still very hard to see exoplanets. First, think about this. Why did it take so long to discover the first exoplanet? Well, let's say that there was a light bulb at the far side of that room you're in. Go ahead, turn around and picture it. Actually, I'll just show you one. Good. Now, wait. That's too big. At the other end of the room, it would look more like this. Now let's say that there is a horsefly. Oh, come on! Okay, better. And maybe just a bit smaller? Perfect! So this horsefly is buzzing in circles around that light bulb. You can see the light bulb clearly, and if you squint, you can faintly see the fly as it passes in front of the light bulb. The process of spotting an exoplanet is similar to spotting that horsefly. However, given the enormous distance to other star systems from our solar system, looking for that horsefly is not like looking across a room. Instead, imagine that the light bulb is 6,500 miles away from you, which is roughly the distance from New York to Tokyo. Now try to spot the horsefly buzzing around the light bulb. That will take some serious squinting. So, if spotting exoplanets is so difficult, how have scientists been able to confirm the existence of over 3,000 exoplanets already? So, scientists have been using a number of methods to detect exoplanets. One key method is called the transit method. We'll focus on that here, so remember the name. Transit method. Transit method. Transit method. Remember how I told you the Kepler telescope launched in 2009 to detect exoplanets? Well, the Kepler telescope specializes in the transit method. And the transit method, it turns out, is very similar to the way the Regulus aliens observed the planets of our solar system from their home on Regulus. It's also very similar to how you detected objects in the physical breakout. Let's imagine that you have a machine that detects the brightness of a star, kind of like in the physical breakout. You're looking at a star called Zulu Foxtrot, and you find the brightness is 100 brightness units. Brightness units is kind of a mouthful. Let's just say bright bits to talk brightness units. So, the star Zulu Foxtrot is 100 bright bits. Let's also imagine that Zulu Foxtrot has an exoplanet, and that in just a couple of moments, this exoplanet is about to travel right into the path of light from the star to your machine. Remember, if the planet travels in front of the star, that means we are seeing the orbit of the exoplanet edge on. How do you think the brightness of Zulu Foxtrot will change when the exoplanet is in front? Correct! When the planet passes in front of the star, it will block some of the light we see from the star, making it dim. However, since the planet is pretty small relative to the star, it will only dim slightly. Okay, the exoplanet has been traveling in front of the star for a little while now, and now it's about to pass beyond Zulu Foxtrot and continue on its way. New question. What will happen to the brightness of the star when the exoplanet is no longer blocking the star? Exactly! Once the planet moves out of the way of Zulu Foxtrot, we see the full brightness of the star again, which was 100 bright bits. As you might imagine, the transit method detects stars in exactly this way. An important fact about planets is that they orbit in a repeated time period, and the time period is exact. So, if the brightness of the star dimmed for 20 minutes today, and if it dims for 20 minutes in 2 months, and if it dims the same way 2 months after that, bingo, we've got an exoplanet. And we also now know that the planet's orbital year is every 2 months.